This lesson deals with supplemental problem 311. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 15. In our modeling of the first quadrant of the I sub c versus VCE curves, we had an edge condition where active and saturation overlapped. Let's take a look back at Chapter 3, page 16, and see if we have the same condition. Right here, if we were to operate right at this point, we would be at the boundary of the active region and the saturation region. They both were with base currents greater than or equal to 0 and a turn-on voltage between the base and the collector. Can we model this condition? The base collector equal to base collector turn-on voltage. The base current was greater than or equal to 0. The collector current was less than or equal to 0. But now VCE is equal to VCR sat, and not just less than or equal to it. And the emitter current, minus I sub E, is now equal to beta R I sub B instead of less than or equal to. Probably easier to use two batteries to get these two conditions. And I'm just going to label that the emitter current is minus beta R times I sub B. This current's already defined, but this one could be positive or negative, so we need to check whether it's greater than or equal to 0 or not. If it's not, then this is not the correct model to put in. P and P would be the same model, just simply reverse the direction of all currents and reverse the direction of all the voltage sources. I flipped the model over because of how we draw the P and P transistor. We also, in our first quadrant modeling, we had an edge of cutoff condition. This is where the active model and the cutoff model overlapped. Take a look at that. Let me erase this dot here. That's this point right over here. And when we're along this axis, so along here. If the base collector equals the base collector turn-on voltage, not just the inequality now, we're less than or equal to 0, and the base current and the collector current are 0. We can model this with a battery, but with no current. We're going to label it with no current. And the voltage across an open circuit, we need to check that it's the right inequality. It needs to be less than or equal to 0. So we're starting at 0 and working our way to the left on that VI characteristic. For the P and P, the model is the same. We just simply change the subscripts on the voltages and then reverse the currents, although they're at 0. And again, this is fixed at 0, but this is positive or negative. We need to check that it's less than or equal to 0. Let's do an example. Take a one transistor circuit with two 1K resistors, a 5-volt battery, but now let's unspecify this. What value of VE would bring the transistor to the inverse edge of saturation if the base collector reverse voltage is 0.72 and the collector emitter reverse saturation voltage is minus 20 millivolts and beta R is 4? Our first step is to put the model in. Between the base and the collector, we've got the turn-on voltage of 0.72, and between the collector and emitter, we've got the saturation voltage of minus 20 millivolts. Label I sub B, and then label that I sub B is minus 4 I sub B. Now let's try to solve for this voltage VEE. Let's go around the loop this way. Rising voltage is 5. I have IB times 1K, 0.72. And then the current in this resistor is going to be I sub B plus 4 I sub B, or 5 I sub B, times 1K would be the drop in this direction. To solve for I sub B, it's going to be 5 minus 0.72 and divided by 6K. And that's 713 microamps. The collector current is minus 5 times I sub B. 5 times this would be 3.565 milliamps. And the voltage V then is going to be equal to I sub C times 1K, but with a sign change because we're looking at this node voltage. 2 minuses cancel, and I get 3.565 volts. I can solve for the voltage VE. The rise in voltage here would equal the drops around the loop. This is equal to a minus 20 millivolts, and then plus V back to ground, which is 3.565. So it's 3.585 volts. Should check that I sub B is greater than or equal to 0, and it is. Our assumption of inverse edge of saturation is correct. And this is supplemental problem 311.